So, well, yesterday we wrote down the polar form of a complex number. That was this thing that looked like z equals r e to the I theta. And I want to talk a little bit today about the geometry of complex numbers, which this polar form is going to make much easier. Now, there's a lot to say about the geometry of complex numbers, and I'm only going to say a very, very tiny part of it. But it'll be good enough for what we need. And then the second thing that I want to talk about is very much related to the first part, which is a formula called de Moivre's formula. And this is really nothing too major after what we've already done. But it's worthwhile and is given a name. Okay, so let's just quickly recap. So, if you start with a complex number, which we could write in the form z equals a plus bi, this is the so-called analog of rectangular coordinates. Right? If you try to graph this, okay, well, this is your real axis and this is your imaginary axis. And you just go A units on the real axis and B units on the imaginary axis and plug this point. And the way you label this point in the, well, if this was R2, right, the Euclidean plane, you write this as A comma B. But since this is the complex plane, you denote this by, well, A plus BI. And of course, we can draw this vector going from the origin to that point A plus BI. And this vector has a magnitude. So the length of this was the square root of A squared plus B squared, which we get by the Pythagorean theorem, for instance. And so, well, if we remember that A plus BI is our point Z, then we wrote this distance as the norm of Z, right, or the magnitude of Z. All right. Then we also notice that once you know the magnitude of this vector, then this point is also determined by, well, you take the magnitude and then you look at the angle that this line segment makes with the positive x-axis. If you know this angle and you know how far out you have to go, that also completely determines this point. And that gave us a different way of representing the point. And well, then we notice that if you actually took, say, this over here to be the unit circle, so this is length 1, then this point right there corresponds to the complex number e to the I theta. And so if you want to go out to this point over here, well, all you have to do is multiply by the magnitude of z. And that'll give you the point out here. And so this point here in polar form is the magnitude of z times e to the I theta. So in general, we can write this z in two different ways. And you can just use trigonometry to work back and forth between these, up to one little detail, which is that, well, this theta is actually not unique. Right? You have infinitely many choices. Right? You can get all the different thetas by adding 2 pi's up here. Right? Replace theta by theta plus 2 pi, or theta plus 4 pi, or theta plus 6 pi, or theta plus 8 pi, or you can subtract 2 pi's. Right? That always just takes you around the circle. Okay, so how to use the trigonometry? Well, we already know how to get from, say, a and b to the norm of z, right? Just use this formula. And, well, how do you get the angle? Right? Well, yesterday we saw that, okay, well, if you know a and you know b, right? B is the height, a is the width of this triangle. And so you can just take the arctan of b over a. Right? So theta could be the arctangent of b over a. At least this is one possible theta. Now, we're going to, well, let's write it down now. All right, we're going to immediately come up with a convention to deal with this problem of there being too many thetas. So, if we write z is equal to, well, let me just write r here instead of norm of z, but it means the same thing, right? It's just the length of this vector from the origin to z. If I have z equals r e to the I theta, this is also the same as r e to the I theta plus 2k pi, right? Where k here is any integer. Okay. Just any multiple of 2 pi will work. Okay, fine. So which theta should we default to? That's the question. I mean, if somebody says, I have a z, it's a plus bi, can you give it to me in polar form? Well, you can use any one of these, right? There's infinitely many of them. Is there one that we can agree to default to? And the one that we agree to default to is the one between, well, in radians, minus pi and pi. Okay. So the angle could be anywhere in here. That, just as if you didn't go around. We're going to, the one we agree upon is the one where you don't have to go around more than once. And in fact, what you do is you go up and you stop here. Okay, so we'll take all the ones from 0 to pi, but we're never going to go past pi. If there's something that was going to go past pi, an angle here, we'd prefer to go backwards. Okay, so we're going to go, so, by the way, so we're going to give a name And where is it, right? What's the angle? You just add the angles. Right? So here's theta 1, there's theta 2. If you add the angles, well, you're going to get somewhere like there. Right? There's theta 1 plus theta 2. Right? And then the length, well, I have to multiply R1 and R2, so this might have to go out quite a bit. Who knows? Depends on how big R1 and R2 are. And so this then would be R1, R2, e to the I, theta 1 plus theta 2. That's a much easier way to multiply it, I think, right? Okay, so this is part of what I'm talking about when I say the geometry of complex numbers. This is one part of the story. This is not so bad, right? And this is going to be relevant at the end of the day when we talk about de Moivre's formula. Any questions? Let's do a little more picture understanding. So, what if I have a vector, and let's go back to regular rectangular-like coordinates. I have a plus bi, and I have another one which is c plus di. Now, if I want to add two complex numbers, this is very easy, right? You just add the real parts and add the imaginary parts.
Like vector addition.
It's exactly vector addition. It's exactly vector addition. So, to draw that, what happens, right? Well, you just effectively, you add this real part up here, but then you also are adding the y part. So basically, you take this vector and put a copy up here that ends at this point. Just put a copy up there. And it should be, if these lines extended on to infinity, these would be parallel. Okay, and when I do that,
Parallelogram.
yeah, exactly, right?
In physics. I took physics like 3 years ago.
And so what I get, if I draw the diagonal of this parallelogram, I'm getting exactly the vector that corresponds to a plus c plus b plus di. So geometrically, the way I can add two complex numbers is take these two sides of a parallelogram and complete it to an entire parallelogram. The really neat thing about this is that you can use this geometric interpretation to prove things about complex numbers by using just pictures, right? Things you know about geometry. The reverse is that if you have questions about geometry, you now have a language in which to phrase them, right, using complex numbers. And you can prove things about geometry using complex numbers. So this is a really important part of mathematics where you take two seemingly disparate subjects, you show that there's a connection between them, and then show that because of that connection, you can step outside of one of the subjects for a while, manipulate in the other subject, and then come back and actually get an answer to your original question. This is one of the most fruitful activities mathematicians engage in. All right. What should we do about subtraction?
It's the same deal, right?
It is in the sense that it's just like with vectors. Right? So what's the answer with vectors? So let's go over here and do some subtraction.
Well, you negate one and then add them.
Right? In math, you never want to do something if you can reduce it to something you've already done. Yeah? Mathematicians are very lazy in this sense. If I want to subtract c plus di, well, this is the same thing as adding minus c minus di. Okay, so minus c minus di, well, that's just taking this and running it in the opposite direction. Right? You just reflect it across the origin here. This down here is minus c minus di. And so if I want to geometrically picture this vector minus this vector, I first reflect it, and then I add these two vectors. Right? So I have to now draw the parallelogram. There's my point. Okay, and so this is my a minus c plus b minus di. So it ends up down there. It's supposed to be some sort of an arrow. Like with vectors, which you guys don't really know yet. But some of us.
It's physics.
It is part of physics, that's right. Actually, in your physics class, maybe they talk about vectors at some point.
Yeah, they do.
Okay. Okay, so this is a nice thing. Fine. So now I want to get to this question from the homework. So, okay, yeah.
Why is not the a plus bi and the minus c minus di, those 2 points connect together?
These two?
I mean, the other two.
Say again, which point?
A plus bi, that point,
Mhm.
and negative c minus di, that point. These 2 points connect together will be the answer, shouldn't it?
So these 2 points connected. When you take these 2 points, draw the parallelogram that they form. That's the answer. But I'm not answering your question.
Not directly.
No, you mean
line?
like this?
No.
No, because remember what you're doing is you're always trying to get back to a situation where you add. Okay? And the way you add is not by drawing a straight line between them, right? But by connecting them to the parallelogram. Okay, now there's the reason why my answer is the way it is, and why your answer is not actually why there's some merit to what you're saying, is that I'm trying to always insist that the vector that I draw to my point is originating at the origin. Okay? When you study vectors, you see, well, I can actually move these vectors all over the place, and you don't actually care that they start at the origin. Right? You can move them, as long as you don't rotate them or stretch them, they're the same vector no matter where they are. Right? In this case, well, if you just drew a line from here to here, right, this, certainly this is going in it's a vector in the wrong direction, it's got the wrong length, so it can't be the right answer. But what you should try to figure out is, okay, well, if I move this over and down, what is it actually telling me? What is this vector giving me? And it's not, this does have significance, but I'm not going to answer that right now. Okay, right. So let's go back to the real number line for a second. So the real number line, things are very nice and easy. Paul, you're taking real analysis right now?
Mm-hmm.
Yeah, you see, doesn't it look much easier compared to all this? Nice.
I doubt I'll ever see real analysis like that.
Well, here's something in real analysis that you are definitely going to see if you haven't seen it already.
You sure?
Absolutely, you'll be using this.
Using it or seeing it?
Well, I don't know. I don't know if Jack likes to draw pictures, but
He likes to draw. This is A. Like, yeah.
okay.
Sets.
All right. So what's the distance between A and B? You guys should know this very well.
absolute value of b minus a.
Uh-huh. The absolute value of b minus a. It's how you tell the distance between two real numbers, right? You subtract them and take the absolute value. Why the absolute value?
Because distance is not
Distance
always.
is positive, right? You always want your distance to be positive. All right, so that's our intuition, that if you want to know the distance between 2 points on the real number line, you subtract them and take their absolute value. And this is where you start to see that the notation is set up in such a perfect way. All right, if we go to the complex, well, we don't have a line anymore, complex plane. So now we have this. Okay, and I have a point here, let me call it Z, and I have another point over here, let me call it W. And I want to know the distance between Z and W. What's this distance? Well, let's see. Let's give names to things. How about Z can be A plus BI, and W can be C plus DI? So, what's the distance? How do you compute the distance between 2 points? So there's a formula. It tells you distance.
Change from A to C over the change from B to D.
Yeah, we could set this up as a right triangle, right? And just use the Pythagorean theorem, right? Or which is exactly how you prove the distance formula, or just say we're using the distance formula. Either way, right? The point is that you're going to say, okay, well the distance. I'm going to use D for distance. The distance between Z and W is, well, it's going to end up being a square root, all right? Because it's going to be the hypotenuse of this right triangle that we built. A minus C squared plus B minus D squared. Note, however, that this is exactly what, I mean this, if you did A minus C and B minus D, that's subtracting Z minus W. Right? If you did Z minus W, you get A minus C plus B minus D. I, of course.
So you could do like the norm of Z minus W.
Exactly, right? What's the norm of Z minus W? Well, it's just the square root of the real part squared plus the imaginary part squared. Which you notice is exactly the same thing as our distance of Z to W. So we can actually get rid of this notation, which I introduced, D of ZW. We don't need it anymore. The distance from Z to W is just the norm of Z minus W, which is exactly the same, right, as in the real number line. If you want to know the distance between two complex numbers, you subtract one from the other and take the norm.
Well, that makes sense because before we've been starting at 0. This is just not starting at 0.
So that's exactly right. This, in the special case where W is 0, we exactly get the norm of Z, right? Which is what you wanted. So that means, let's say you wanted to know all the points satisfying the following. Norm of Z minus 2 is equal to 3. What this means is, well, the distance between Z and 2 is 3. So you have a point on the complex plane, which is 2, right? It sits on actually the real axis. And you're looking for all Z's which are exactly 3 away from this. Well, let's see, here's 1, let's see, 3, 4, 5. Okay, 5, that's exactly 3 away. And let's see, 1, 0, minus 1, that's exactly 3 away. What else is going to be exactly 3 away?
2 plus 3i.
Sure, I can go up here, right? Up to 2 plus 3i, that'll do it. In fact, what kind of shape am I going to be able to make?
A circle.
So what is a circle? Circle is just a collection of points which are a fixed distance away from the center of that circle. Right? You choose a point in the plane, say, okay, what are all the points that are 6 units away? Well, that's a circle with radius 6, centered at that point. So you can, okay, this is a really lousy circle. Okay, and this, what's the radius of the circle? It's exactly 3. So if you have a more complicated setup, where you don't have this immediately, the goal is to put it into this form. So for instance, you might have something that looks like 3z minus 5 equals 18, right? So the norm of 3z minus 5 is 18.
Divide by 3.
Divide by 3, right? Now, there's something that, there's a property of this norm that I don't think we've stated explicitly, but which we would need to proceed here. And the property is that if you have a complex number z, and you just multiply it by a real number, and then take this norm, it's the same thing as if you take the norm of z and then multiply by the complex number. Okay? This is useful. Okay? How hard is it to prove? Not hard at all. Right? If you wrote z as x plus yi, then you'd have the norm of az equals the norm of ax plus ayi, which is equal to the square root of a squared x squared plus a squared y squared. Now you can factor out an a squared and then pull it out of the square root. When you pull it out of the square root, it's just an a. So this is a square root of x squared plus y squared, which is a norm of z. Okay, so it's not hard to prove at all. Okay, so using this tells you, okay, if I factor out a 3, I can get the z by itself, which is advantageous because I want to get it back into this form of z minus something. So this becomes 3z minus 5/3 equals 18. Divide by 3, z minus 5/3 equals 6. And so geometrically, this is saying take all the points around 5/3 that are exactly 6 units away. Okay? Or maybe a better way to say it, take all the points that are exactly 6 units away from 5/3. Now, of course, there's nothing special about the fact that I had a real number here. This could have been a complex number. This could have been 5 plus I. And then this would have been 5 plus I over 3. Okay, so you'd said, okay, fine. Look at all the points that are exactly 6 units away from 5 plus I over 3. Okay. So the trick on some of those homework problems where you're having this, right, is to try to get it into this form. Into this norm of z minus w.
So when we're actually writing an answer, do we want to draw a circle or?
I mean, I would draw a circle to show it. I would also, I mean, I would say it in words, and I would draw a circle.
We don't have to graph it though, do we?
I mean, I would. It's.
But we don't have to.
I'll leave it up to your conscience.
I have a question though.
Yeah.
On the first one where you were saying that the imaginary is -2.
Okay, yeah, this is a different kind of. Yeah, this is a different.
No, I just have a quick question. Wouldn't
Yeah.
it be just like all the lines that intersect that point?
It's, well, there's not all the lines. There's exactly one line.
It's like saying y equals.
Let's take a look at that.
But aren't you just saying that the imaginary value is -2? So wouldn't
Exactly
the
what I'm saying.
Yeah, but the
But wouldn't-
imaginary value doesn't change, so.
So
You have
z is
all just
equal
real values.
to a plus bi, but the imaginary value of z is minus 2. Then this means it's actually a minus 2i. Right?
Okay.
So now when I try to plot this, I'm saying, okay, what are all z such that they look like a minus 2i? Well, minus 2i is down here, and then the a can be anything, right? So I'm allowed to go anywhere. So it's going to end up being this horizontal line.
Yeah.
Those are all the points where the imaginary part of z is minus 2. Does that make sense? What if it was the real part of z is equal to 3? Well, over here you would now say z is equal to 3 plus bi. And so when you graph that, well, you go, okay, 1, 2, 3. The real part has to be 3, and so all the points for which the real part is 3 are the ones that go through there, through this line. Try to think of the analogs from R2. This one is the same as saying x equals 3. Right? Real part is equals 3. Is just, that's the line x equals 3. This is the same as saying y equals negative 2. Exactly the same.
Now, actually, when I was doing this problem, I had a question because with your, how would you write that line? Would you say I equals negative 2?
Well, no, you say imaginary part of z equals negative 2.
So that, okay. Alright.
Okay.
That's exactly how to write it. Yep. Oh my. Hold on. Go on. You had a question?
Yeah, see.
Oh, I'm not going to tell you how to do C. Now I've given you the.
See. No, but now that I'm looking at it with what you've given me, I still don't know how to solve it.
That's right. You have to fiddle with that thing. That's the hardest one on there. You have to fiddle with it to get it into this form, and it takes a little bit of work. It's possible, but it's good. It takes some work. You have to.
Okay, never mind.
Okay. Good. Teach a man to fish. So forth. So on. Okay. Let me quickly finish, because we only have a couple minutes left, with Dubois' theorem.
Oh, yeah.
Because then.
Yeah, because we did that the other day. That's right. Okay.
Alright, so this part isn't so, this is not going to be so earth-shaking. It's quite nice. Well, so I want to know if I should state this. I think I just state this for, just for natural numbers. So let's say I want to, let's say I want to take a complex number z and raise it to the nth power. And for now, n is just a natural number. Well, I know that I can write z as its magnitude times e to the I theta, where here theta is the argument of z.
How do you say that name?
Is that a
Dumois. This, oh, sorry, this is that's a V and that's an R. I kind of got,
Okay. He was French.
yeah.
Mm-hmm.
Dumois. Yeah.
So easy to tell.
I know.
So we can write our z to the n in this way by just converting to polar form. And then, of course, it's very easy to do this, right? You just put the n in. So you get the magnitude of z to the n, and then e to the I theta n. But then yesterday we saw that, well, e to the I theta is cis theta, right? Cosine theta plus I sine theta. So you can actually write this as the norm of z to the n times cosine of n theta plus I sine of n theta. So this is Dumois' theorem. So if you want to exponentiate a complex number, you can actually, as long as you know the argument and the magnitude, right, you can just write it down explicitly like this. And what's nice is, well, this is just a real number over here. So raising it to the nth power is no big deal. Over here, you've turned exponentiation, which normally is harder, into multiplication. You're not looking at cosine of theta to the n and sine of theta to the n, which might be harder. You're actually reducing it to cosine of n theta, which might be easier. And when we start next time, I'm going to show you a really cool application of this that allows you to write down formulas for things like cosine of n theta. This is just a real question, right? You already know, for instance, that the cosine of 2 theta is cosine squared theta minus sine squared theta. And you know that sine of 2 theta equals 2 sine theta cosine theta. We're going to use this formula to actually come up with formulas for sine of 3 theta, sine of 4 theta, cosine of 3 theta, cosine of 4 theta in a really easy way, just using de Moivre's formula. So that's how we'll start next time. Okay, I'll see you tomorrow.